Okay, I guess it's time to start. Welcome to my presentation. I will talk about landscape visualization today, and even great-looking ones. Whether you find them great-looking or not, that's a little bit depending on your expectations. But at least I will share experience, knowledge that I have in this topic, and then we will see how far we get, how great-looking they are, how detailed they are, etc. I work at Autodesk. I will not talk about Autodesk, I will talk about landscapes instead. But in my work, I do stuff that is related to this. So that's how this is relevant in my everyday work. So I work as a developer, software engineer, depending on how you look at it. But yeah, I write code every day. In this talk, I will focus on what we can build ourselves. And also, depending on which data you have, what you can achieve. I will focus on what's open and free out there. So I will not use that many commercial data sources. I will mention some, but not that many. So the focus here is being a developer, what can you actually build yourself? So some introduction to this topic. I will talk about visualization, and that's a huge field. There are so many things you can do with visualization and visualizing, yes, data. And it encompasses many different subtopics. One thing is the data gathering. You need to have data in order to visualize it. You would like to do some analysis on those data, perhaps. You would like to present them properly in terms of how the design or the concept the concept presentation should look like. And also you're depending on computer graphics, the ability to draw stuff. As this field has progressed, we have seen quite a long evolution from the early beginnings in the 60s until now, with a lot more powerful hardware. We have a lot more data available for us, which is open. And so you are expecting more details and high realism all the time. Right now, in the terms of landscape visualization, games are a very interesting field where a lot of things are taking place. Landscapes are huge. They contain a lot of data. They can be very detailed. And still you expect to be able to move around them freely, in this case from Zelda. Unreal from Epic Games has pushed the boundaries here. Their 3D engine using this technology called nanite is extremely advanced and can give very, very, very detailed landscapes. Here down to the grains in the sand and the small straws, things like that. It's getting harder to separate photos from 3D graphics. Also, we see a different field. This is actually an illustration from approximately where I am from. I'm from Molde in Norway. And they're about to build some bridges, maybe. It's a big discussion, it's a big topic. But at least you can use landscape visualization to illustrate infrastructure, how things will look like around you. Basically do a model of the world, not inside a game, but replicating the real world around you. So if you want to do landscape visualization, it's important to keep in mind what your aim is. Is it realism? Or is it analysis or like a stylized presentation of some data? Do you want to be photorealistic like the flight simulation games or simulators that we see now? Or you do want to display data inside a context which actually is a landscape? And this guy is an urban landscape with buildings in it. My talk will focus on a little bit of the left side thing, but we will not enter the realism levels that flight simulation games have. They use a lot more data than what is openly, freely available. So I will focus on what we can do ourselves with data that's out there. So yeah, I want to mention this. Why do this yourself? Because I think it's 2 or 3 weeks ago maybe, Google released 3D tiles from their mapping service. And this is essentially very, very high quality data that is available under a certain limitations. I mean, Google has produced this data. They sit on a big, big, big treasure trove of data, which is extremely high quality, nice, valuable, all those things. But I will not spend that much time on this as such. Feel free to experiment with it and use it and learn from what they are doing. Of course, what Google does is normally technically very, very high level, very, very skillful people, of course. But there are some cons here. This functionality or system or tool is still in experimental stage. It's very interesting though, but it means this is essentially a prototype. So if you want to make something that you can rely on, you shouldn't be using this for the moment being. If you look at what Google means when they are publishing things being in an experimental stage, it means that it hasn't done production, it hasn't come to production level quality yet. It's not covered by any service level agreement. It can take a year or two before they gather it, consider it a production system. And also, if we are to be a bit negative, Google has a certain history of suddenly deprecating stuff. So if you rely on it and it's gone, it's not so fun. So it all depends on how independent you want to be, what kind of flexibility you want to have, and basically the control you have. So there is a trade here in terms of control versus amount of work you have to do yourself. But feel free to experiment with this. This is great stuff, absolutely. So back to landscape visualization. I would like to describe this as a topic where you have increasing detail. You have layers, and when you add data belonging to a certain layer, you increase the detail levels. And so we can start with the terrain as such, the terrain surface. That's normally basically just how the shape of the ground is. Also, you need to take into consideration water bodies, like you have a lake or a fjord or something like that. That's very flat, of course. It doesn't add that much detail, but it has some nuances when you process data. And of course, you can add surface color on top of this, basically a photo that you drop on top of the surface. And that gives you a lot more detail. And then you can start adding objects, three-dimensional objects, basically meshes that you put on a certain location on the terrain surface, normally. Typically, you start with the large ones, buildings and bridges and things like that, and you can add smaller and smaller ones to increase the detail level. Basically, the infrastructure is typically the next level, roads, railroads, power lines, etc., and vegetation might be the last one, depending on the context and how you want to use this thing. Of course, when you start adding vegetation, such as trees or bushes or grass, the detail levels skyrocket. And you have to spend a lot of CPU or rendering capacity on small things. So the detail level you are working on will, of course, decide what you want to focus on. But this is the typical structure I would look at this. And when you do these things, you encounter a lot of various data structures. When you're talking about the surface color or also elevations, as we will return to, it's basically raster data. It's basically an image, and with values inside you can treat like pixels with a certain intensity. When you talk about surface shape, sometimes that's referred to as a 2.5D mesh. It's two-dimensional in a sense that it's flat, but there are variations on that elevation level of it. But it's not 3D, because if you imagine a line going from top to bottom inside the geometry, you only intersect it once. And that's one way to look at something that's 2.5 dimensional. It does have variations in heights, but it doesn't intersect the object twice. So you can imagine like a carpet or a rug or something that has some waves in it, basically. You will also encounter true 3D objects, buildings. And for instance, something like roads can be either represented as two-dimensional. Imagine looking at the map from above, then you just have one line which says there's a road here. And if you increase the detail, like in this illustration, the roads suddenly are three-dimensional. They intersect with the landscape, and they have a certain width, they have a certain height. You have gravel outside of the road, etc. And sometimes you want to render vegetation as point clouds. Basically small dots with colors in them that can signify leaves or something that's very, very, very small. In this case, these trees, I don't know if they are point clouds or not, maybe not, but you can also imagine that they are just tiny dots. They don't have to be anything complicated as such, like a triangle or anything like that. It can be just dots. And that's because when you gather this data, most of those gathering processes, they start with gathering point clouds already. So if you just visualize point clouds, you don't have to do that much processing in between. But point clouds, they are very hard to visualize in large numbers because they represent only small things, very, very small things. So if you have large surfaces, then point clouds are not that ideal, maybe. Okay, that's data. But whenever we talk about geographical data and GIS systems, we need to also talk a little bit about coordinate systems. This is a complicated topic, so I'll do this quite simplified here. There are two basic types of coordinate systems. We have one on the left, which is based on covering the entire world. And this is something that most of you likely know from before. It's basically the latitude and longitude, like a spherical coordinate of a location. What's interesting here is that the unit of stuff is degrees, and that doesn't really translate to distances in the real world easily. So there's a drawback with that. But it's very commonly used, of course. On the other hand, this is the coordinate systems I prefer working on for small areas. I use then a UTM zone, and a zone in this case is a smaller area of the globe. And each of these zones, they have names and numbers to them that identifies them. And then inside such a zone, we pretend that the Earth is flat. That's a very controversial topic. You know, the Earth shouldn't be regarded as flat. But on a small scale, let's do that. So the UTM-based coordinate systems, they are easier to work with in practice. Then the unit is meter, and that's very nice for us. And then you can treat any location as an XY coordinate in two-dimensional. And the coordinate is relative to some reference point. Typically, I guess it's the left bottom point inside a zone. And that makes things easier. Because it's a coordinate system, you are quite used to reason about, essentially. X normally goes to the right, meaning eastwards, and Y normally goes to the north, up. So that's not so hard to translate. And then in that case, Z goes up in elevation, which can be the same as the graphics tool you're using, or it can be different. Yes, every graphics tool has its own convention regarding what's up and things like that. But at least the UTM coordinate systems are nice to work with. So then we have data types, we have coordinate systems, and we need to talk about data providers, because you need geographical data to have something to display. So the typical data providers that are out there, there are like three big categories. You have the crowd sources one. They are typically based on people entering data as a hobby, something they're interested in. The most typical example is OpenStreetMap. That's a huge data source. You can cover most of the world. There are some locations where there are not that much data. But for Europe and the US and most of the world, otherwise, they have a lot of data there. Roads, buildings, mainly two-dimensional things. The data are two-dimensional, mainly. I'll get to that. But the data is free, but you do need to attribute them. That's important. Those are people that are doing this for free, and they want credit for the work they have been done, of course. That's natural. Then you have the governmental one, the national providers, typically. In the US, that's the US Geological Survey, USGS. They have lots of data, and that's interesting. All of the governmental data in the US are in the public domain in the normal situation. So you're free to use them. You don't even have to attribute them normally. I mean, if it's nice if you do it, but it's not strictly necessary under their data license. In Norway, we have Kartverket, the Norwegian Mapping Authority. They have lots of data. Most of it is free, but there are some data sets that are paid. And then outside the scope of this presentation as such. And then you have research projects that sometimes provide data across the entire globe. Some examples there are EU, their Copernicus project delivers great satellite photos. I will get back to that. NASA also has done some research projects that give terrain models of the entire world. They have the SRTM and the ASTER datasets are two examples of that. Those are basically satellite names or project names that provide data. So there's also a mix there of free and paid data, typically depending on resolution. High resolution data might cost something. The lower resolution data is usually free. So these are the data providers you typically will interact with, one of those categories here. And you will also meet quality problems. Oh, yes. If there's anything to say about geographical data, you will meet issues. Definitely. You will have areas where there is no data, and you need exactly the data that should have been there. You have errors. Here's one legendary example from the Microsoft Flight Simulator, the release, I think, 2 or 3 years ago. They were relying on OpenStreetMap buildings and building elevations. And I think this is some spot in Australia, in Sydney or something. And there was a building with 212 floors. It was a typo. The person that entered building heights accidentally entered 212 when it should be 2 instead. And nobody noticed, because the data sets are huge, until somebody just flew across over that area and see here, there's a nice monolith here. And it has even 212 floors. I mean, this is accidental. It's easy to spot, it's easy to correct. But there are a lot of cases where you have data that is wrong and you don't know it. And that's much tougher. If you want to build something that people can rely on and you have uncertain or unknown data quality, that's not so nice. So there is trade-off here. The data are free, but you don't necessarily have any guarantees on them. And there can also be inconsistencies. Resolution, I mean, you have to rely on low resolution data. And also there are some properties that you'd like to have which are not available on the datasets. One example there is typically building heights. In OpenStreetMaps, some buildings have heights, others do not. In some situations, you have the number of floors, like here, but you do not have the height. Okay, then you can do an estimation. If it has 10 floors, it can be something around 30 meters. But if you don't have the number of floors either, okay, what do you do then? Maybe you just set a default height. We don't know, so let's assume 4 meters, maybe. And this will then influence the richness you can do in your presentation or visualization. Okay, let's get started. Let's build something. We will build a terrain surface. To the right here, I have taken a photo, I don't know. It shows data, it shows elevation data. This is typically encoded in a file format called GeoTIFF. A TIFF file is essentially just an image file, like a JPEG or something like that, but the compression is lossless, normally. And inside a GeoTIFF, you have elevation values, here seen as varying intensity levels. So the brighter any pixel is, the higher up in elevation it is. So the dark spots here are, as you might think, fjords, water bodies with 0 elevation. So this is some spot in Norway. And inside a GeoTIFF, you have information about where the data is. That's typically the coordinates of the bounding box, like the corner points. Where are they located in the world? In a certain geographical coordinate system. Can be any system, but it's also explained which system those coordinates refer to. That's important. And also the GeoTIFF contains resolution information, what's the distance between each height value, and then the values themselves, typically heights in meters above sea level. They are normally stored as floats, so you can have a large range. Tools, libraries to use for processing such files. There's one tool which is very, very good. It's a bit complicated, it's command line driven. It has an endless array of parameters and different subtools. It's called GDAL, but it's a brilliant tool. It can solve anything, I would say, almost. So, although it might be a threshold to start getting into this, I will still recommend it if you are to be working with geographical data. Have a look at GDAL. Please do. Okay, so you can script things using that. But if you want to integrate something tighter with your code, then for GeoTIFFs, here are 2 examples of libraries. There is one called geotiff.js for JavaScript and TIFF file for Python. Those are the two languages that I mainly work with, so I will refer to libraries or tools using either of those two languages. So yeah, GDAL or GeoTIFF or TIFF-file can process and extract information from GeoTIFFs. So what do we do? Well, we need to look a little bit more into the detail of terrain sources. So in Norway, you have Kartverket, Norwegian Mapping Authority. They have lots of terrain data. You can go to this URL, Kartkatalog, to browse through the data sets they have, and they have a lot of stuff. You can also go to høydedata.no for UI, for search. That's the illustration to the bottom right here, where you basically can select a rectangle and then order data, and you will get a link in your email where you can download the process data. So you can order it on demand and have a good visual experience in deciding what you want to download. In some cases, like in the upper right, the data are pre-processed and available as tiles, as certain areas that you can work with. So it's maybe sometimes easier to just pick one tile and download that, and then work from there. There are also APIs, lots of HTTP-based protocols for integrating with map data. So there's one thing called the VMS, Web Map Service, I think it's named, where you basically create a URL, which can be tremendously long, have lots of parameters to it, and you do a GET request against the server, and back you get a GeoTIFF file. So if you want to write code, that can be a good way of doing it. Terrain sets, global sets, are available from NASA. And the downside about those data sets is that normally for global data sets, they are, digital surface maps. They do not encode the ground level of things. They include buildings and vegetation. So if you have a flat area where you know the ground is flat, but there are buildings on them, they are normally so low resolution, like 30 meters between each point, that the terrain will appear to be very wavy. And that's the reminders of the buildings that you see. So it's the surface that you see, it's not the ground level information. So whenever you want to display landscapes, you want to look at the terrain and not the surface. So that's called a DTM. So you see here, global and research, there is something called EDTM. That's a data set where they have been trying to use machine learning to remove those artifacts from buildings and vegetation. So that's a true attempt at a true terrain surface that is global and that has 30-meter resolution. So the link is tremendously long, so I just say search on Google and you will find it. There is not much else that is referred to as EDTM30. For EU, you have datasets also here provided by Copernicus project. All of these are free. Most terrains are free. A few of them require attribution. So what do we do? Well, we need to prepare the input data. Get hold of a GeoTIFF from the providers, convert from any other system to the UTM coordinate system you are working on, like for your project, and crop to the desired area if the data aren't already cropped. Then we need to make a triangle mesh out of those elevations. I would deeply recommend that you simplify the mesh to reduce the triangle count. I'll show that in a moment. And you can, for example, store it as an OBJ file. That's basically just a mesh format that's simple. So here, on the right side, we have an illustration of a GeoTIFF. The red dots are the bounding boxes in geocoordinates. The gray dots are the elevation values. And what you basically do is you make triangles across those points in a regular grid. Not too complicated. I wrote some code that does this. It's available in a GitHub repository. I will show you the link further on into the presentation. So read a TIFF and just connect dots with triangles. And then you read out the elevation values inside each dot and then make triangles with those elevation values as the coordinate points. So it's not too difficult. And then comes a difficult thing, that's mesh simplification. What I've been using for terrains are basically two different techniques. The first one is called quadric mesh simplification. This was the result of a paper, I think it was written in 1999 by two people. that describes how to simplify geometric data. It's a very good technique, no problem about that. It applies to general polygon objects. And so you reduce triangle counts without affecting the detail that much. You try to remove redundant information, essentially. The thing is, sometimes the technique can go wrong. You don't have any guarantees against geometric problems. Like you have duplicate points, duplicate vertices, or you have triangles that overlap, and you don't want triangles to overlap. In a terrain surface, like in the previous slide here, you want the triangles to evenly or to divide the surface. So they always share, or you split up the surface into, I would say, partitions, if that name makes sense, and not have triangles that might go on top of each other. But using quadratic mesh simplification, you might end up with exactly that, triangle overlap. So, before the two guys that made that paper, 4 years before that, they made a different paper, which is called fast polygonal approximation of terrain and height fields. And that technique, I find, is a lot better. It's limited to terrains, but okay, we are working on terrains anyway. It's easier, it's faster, it's less resource demanding, and it gives great geometry. It does divide the terrain surface into a partition. And you have no triangle overlaps and no duplicate points. That's good. And also, there are quite a few implementations of that last technique. Here are 3 of them. One is C++ based, one is in JavaScript, and one is in Python. So you have lots of good available tools for this thing. Often, with terrains, you can reduce the original triangle count quite a bit. You can reduce down to 10% or something, and still have reasonable detail. And then, of course, you save a lot of resources in your GPU or on your machine that you can then spend on other things that are more detailed or more interesting. So here's an example of a simplification that has been taking place. So there's a great tool with the URL polygon.love. We love polygons, don't we? And then you can drop 2 GLB files, essentially mesh files, and you can do a visual comparison of them. So let's see if I can do this. Yeah. This work? Yes, it even works. So here I've done exactly that. We can see here on the right-hand side, this is a polygon, a mesh having 35,000 polygons, triangles in this case. And here we have a little bit more than 1 million triangles. And from this distance, there is no obvious difference to this. We can even go quite close. And we see here, using the slider, that, okay, there are some differences, but really not that much. Let's look at how things look when we see a wireframe. So, look at the difference in vertex density here. Why do you want your GPU to struggle with all of these points when you can just use these points instead? And here I think this is something like 5% of the original data density. The thing is, this happens because the terrain in itself is oversampled. There are too many sample points than actually what the terrain needs to be properly described. But this is the case often. So be aware of that. Detailed data doesn't necessarily give you more information. In that sense, the information can be redundant, so it can be simplified away, and you have more resources for other things. So I like this tool. It gives you a good display of how things look like. Okay. Yeah. Let's, oops, sorry. Let's give a demo. I hope the demo ghosts are not here today. Let's see if they are. Yeah, it even works. This is a triangle mesh from an area in Bergen. I've using as an example. I've downloaded a GeoTIFF. I processed the file. I've done simplification using that second approach, the easier, faster, better one, and produced, in this case, I think the end result is a GLB, but it's the same as an OBJ file, meaning a simple, good mesh format. This area is 10 by 10 kilometers. I think there is something around, I don't know, maybe 1.5 million triangles here. But you can still move around quite easily. And here we see what happens when you have a sea, or fjords in this case. You can represent those areas with very few triangles, because it's already flat. So you don't need all those triangles there. And so we can, basically have a look. And somewhere here is the Ulriken, the famous mountain in Bergen, among more mountains. They have 7, I think, that they like to say. I'm not from Bergen, so I'll try not to make fun of anybody here. But it's a nice example, because I was thinking, what landscape do I want to show here for my presentation, where I have sea, I have mountains, and I also have lots of buildings. And then I think, nah, Oslo is boring. Bergen is great. So this is why this is Bergen, in case anybody's wondering. So this is the wireframe, lots of lines, but it still gives a fascinating display, I think. Let's see what happens when we start drawing triangles instead. Shouldn't be that much of a difference. Okay. Normally, actually, drawing triangles is faster than drawing lines on a GPU. So I expect the performance here to be a little bit better. So okay, we can move up close and see there are lots of triangles here. And together they describe the surface quite well. Here we see roads even. It is a quite detailed data set in its origin here. I'm being using 1 meter resolution data and then simplified it to something like, I'm unsure the percentage, but I would expect something like 10% of the original triangle count. And we still can see lots of details, and this area actually is quite big. As mentioned, I think it's 10 by 10 kilometers. So that's how Bergen looks like in grayscale and just the surface. And we see some stuff going on here that seems to be man-made. Let's get back to that later on. It's not just mountains. There are more stuff. Okay. So yeah, again, the code that runs these things are available at this URL. You need to provide your data in order to run the code. I'll do some more detailed documentation of it. The GitHub repo now is quite rough, but the code is there and it works. So I can give some more explanations on how to run the example code there, and then you will be able to run it on your machine. But yeah, grayscale surfaces aren't that interesting. We need to add some surface color as well. Basically, textures. So as a starting point here, you have to have a photo of the area. And this photo has to have a particular property. It has to show the area as seen from above. That's an easier way to understand something called an orthophoto. Let's imagine you sit on an airplane and take a photo out of the window. Of course, your angle is not from above. It's at a certain angle to the horizon. So this needs to be compensated. Although planes that do take photos, they fly directly above, but there's still some angles and some things going on that will not make a good photo for this purpose. So look for orthophotos. They are important. And also, the photos need to have geographical coordinates attached to them, or else you don't know where you are. And these coordinates, of course, has to match the area you are already describing as a terrain surface. So here again, you need to get hold of some information, convert, and crop to the desired area. The nice thing is that oftentimes those photos are also available as GeoTIFF files. So you can basically do the exact same operation in terms of cropping and conversion to make these files match really, really well. That's important. You need to have good matching. But instead of elevation values, you have surface color, normally just RGB values. So you can use the same tools and libraries as before to process most of these texture maps or surface photos. Okay, data sources for those. In Norway, we have orthophotos, lots of aerial photography being done. There is a service called Norge in Bilder, Norway in Pictures, that is available at Kartkatalogen. So go there, do a search. And those data or those orthophotos are free for non-commercial use. That's actually very good. They are high resolution data, something like 10 centimeters per pixel. And that's great. If you cannot rely on those, you can look at satellite photos. That's the best alternatives I know that are open and do not have any restrictions on them. You find it on Sentinel Hub. That's a website for Sentinel satellite data. They're free, okay, attribution is required, but then you are at a 10-meter resolution scale. And that's a lot of information loss there, but it's the best available of open global data for satellite photos. The Norwegian Mapping Authority also, they provide cloudless satellite photos of Norway. That's great actually, because if you take photos from a satellite, if you have a cloud, you will see nothing. And Norway has a lot of clouds, you know, the weather is bad and all of that. So what they have done is they've taken series of Sentinel photos and merged them together. So you cover the entire Norway without any clouds present. That's good. So you can look also at Kartkatalogen and you will find photos that contain all of Norway from a satellite perspective. So what do you want to use? Satellite photos or aerial photos? There are pros and cons. One thing is the resolution. Any photo that's taken from an aircraft has a lot higher resolution than a satellite, basically due to the distance. Here on the right side, we see an orthophoto taken from a plane. The thing is, a plane, okay, it flies fast, but not that fast if you want to cover larger areas. So there's always a risk of one survey meeting another one. So here you see there is a difference in the color on the sea. That's basically because the surveying has been taking place on 2 different days. So the light was a little bit different. You might see also remains of thin cloud layers in aerial photos. So better resolution, oftentimes better color rendering, but you have seams where you see the different data sets where they meet. Left-hand side, we have satellite photos. Okay, you need to have cloud-free days. You have lower resolution, but you have a lot more consistent color rendering of the various data sets. A satellite, of course, can cover a lot of more data in one go. So you have consistency there. The bad thing about satellite photos is they take photos and the color will be affected by atmospheric phenomena, such as dust or water vapor and things like that. So they try to do color correction, and sometimes it's not that good. So here I did some little bit of manual tweaking on the photo to the left to make it match a little bit better to the one on the right. So the colors might be a bit off. And also the resolution is somewhat limited since we don't have access to the really best satellite imagery available if you're looking at open data. I guess satellite photos can also do 1 centimeter resolution, maybe military ones, okay. But if you pay a lot, you can get really high resolution also, satellite photos. But here we are still at free and open data, and then we are bound to, I think it's 10-meter resolution. So depending on how large areas you want to cover, the detail level you need, you can use one or the other. And whenever we talk about imagery, we need to talk about optimization as well. There is this thing about textures. They are images. So if we imagine 2K pictures, meaning 2,000 pixels each way, it has a raw data amount of 12 megabytes. And whenever you want to render stuff, you need to put that texture onto the GPU. So 12 megabytes, these times is not that much, but if you have large areas or high detail level, it can become a lot of data. So in a normal situation, you do compression to a JPEG file, for instance. That could normally reduce something to something like 10% of the original data. So you're at 1.2 megabyte. And then you want to put this on the GPU. So you do that, and when you do that, the data are decompressed, and you're back to the original data. So the use of JPEG doesn't help that much in terms of how much memory you use on the GPU. It's good for transferring the information, but you spend a lot of memory on the GPU. So there are actually some good alternatives here. So let's start again. We have the raw data, you do compression, and now you compress to a different format. There's a format called KTX2. It's part of the GLB standard, meaning a mesh format that also supports textures inside meshes. And the thing is, you can actually compress to the same level as you can with a JPEG. That's not too bad, because JPEGs are really, really good at doing what they're doing. And so, looking at the GPU, you do an upload, little small asterisks. There are always these nice asterisks. Upload, but not quite upload. Okay. But still, the thing is, you keep the same data amounts in a GPU. So you don't spend the same amount as the raw data in this situation. So what happens here is that the KTX2 format is called a universal texture compression format. It's one way of storing raster information in a way that's easy to convert for a given GPU. Because then when you look at what GPUs actually support, we hit the notion that various architectures, operating systems, platforms, etc., they all support different compressed texture formats. And that's annoying, but we don't have to deal with that. We can use a universal format, and if you do this in a browser, this transcoding is really, really fast. It doesn't affect anything at all in terms of timing or resource use. So you compress to KTX2 format, that's a little bit of a heavy operation, but when you upload it to the GPU, the code that does that can translate to a native compressed texture format for you. So it looks at what hardware are you running, and it converts it and uploads, and all is good. And this actually works. It's a great technique. And then you can stuff a lot of more texture information into a GPU than in the other case. So this is a good optimization to do. Okay, let's go back and see some more stuff. Here we were in Bergen, in gray. And let's go back over here. And now, look at this. We have textures. One texture, one big texture. And this adds a lot of information to us, for us. So this actually is, I'm using here now, aerial photo from Kartverket that is free for non-commercial use. This is not commercial use. And then we can look at Bergen in a lot more detail. So this becomes now quite a bit more realistic. So the nice thing about using aerial photography is that you get free light and shading inside it, because it's a photo of the real world. So you add a lot of detail just from the imagery itself. And that's detail that's very hard to compute and calculate if you want to do shading of the geometry yourself. So essentially, having good texture quality will give you a lot of perceived quality in your visualization. And still, this runs quite okay. No big problems here. And we can go quite detailed look at stuff here. Oops, sorry. Yeah, I'm unsure what the resolution here. The source resolution, I guess, was 1 meter per pixel. I needed to make the image a little bit smaller. I think the image here is something like 4K by 4K pixels. I'm unsure. But yeah, look at this. This is not too bad. And it even runs in a browser. Okay, my machine is a little bit powerful, but not that extremely powerful either. And here I'm rendering using Three.js as the rendering API or rendering tool. Yes. Okay, let's move on. We are satisfied with the surface and the texture, but let's see if we can add some more stuff. In this case, I found that buildings are a good example of things to add. You will find building outlines, two-dimensional geometry, on OpenStreetMap. They have building data for a lot of cities, including Norway. And basically what you do then is you can get hold of a GeoJSON file. That's a file that stores in JSON format, as you can see from the name, vertices and polygon information of the outer walls of buildings. So you basically have the outlines, not more than that. Sometimes you have the heights and or the floor count. And the thing is, with GeoJSON, you only support those lat-long coordinates. So you need to convert that to your local coordinate system. And so the tools here mainly are doing that. They can project information from one coordinate system to a different one. Here is one JavaScript example and Python example. And also there is a good viewer called geojson.io, where you basically can drag and drop a GeoJSON file, and it will show you the contents rendered on a map. That's good. Apart from that, you need JSON parsers, which every language has now, I would assume. So that's no big deal. So that's a way to get hold of buildings. Yeah, well, you need to look at, for instance, Kartverket again. They have a very detailed building model of, I guess, all buildings in Norway. Unfortunately, it's not free, so you cannot get any further than that. But you can rely on OpenStreetMaps. And they have a good site, osmbuildings.org, where you can download building data in a more direct manner. I'll return to that in the next slide, I think. In the US, there is also this thing called OpenCity Model, which has, I think, better quality for US buildings. So if you want to do that, then have a look at that URL. Nearly all sources are LOD1 data, essentially not so detailed. And yeah, if you look at the map here on the right side, these red polygons is essentially what you get hold of. That's what you get when you have a look inside the GeoJSON files. But okay, LOD. LOD, levels of detail, in this case for buildings. So this is an illustration that shows the various detail levels that are, I think, are categorized or are standards for buildings. So a 2D outline would be LOD 0. If you have height information, you can say it's a LOD 1. If you have roofs, sloped roofs, it becomes LOD 2, etc. So in a normal sense, you will not be able to go beyond LOD 1, I would assume, at least in Norway or globally. I've seen datasets in German and Netherlands that are LOD 2. So if you want to do detailed modeling of those two countries and the buildings there, you have the option to get hold of that kind of data. So we are getting there, but it takes time. And of course, the data amounts are huge. Having a LOD 2 building is a lot more data than just LOD 0 or even LOD 1. So what do we do? How do we get buildings from outlines? So here's one way of doing it. Okay, let's return to the GeoJSON file. You convert it to your UTM system you're working in. And for each building, you read the outline polygon. That's the thing on the right here. You read out the height, or you estimate it if you don't have it. Then you have the roof. And then you basically create side walls around. And then you triangulate the top. And then you have a roof plane. So it will be very boxy, but now you have a three-dimensional mesh object out of what used to be a 2D outline. That's the way you do these things. That's the way you can build something that resembles a building from 2D information. You can add more things by guessing, or I guess machine learning, of course, gives options, but this is a simple way of doing it, and it adds detail. And then you can store these things inside any mesh file object, for instance, an OBJ file. Okay, so how do we get hold of these building GeoJSONs? Well, go to the website, OSM Buildings, and then you can see the map area you're looking at. It's divided into tiles. And so on that site, they store GeoJSON files containing the buildings inside each tile. And then you have to figure out the pattern, how they describe tiles, and map that to a geographical location. So if you go to a different website called MapTiler, you can find out the tile numbers. And on the bottom here, next to the bottom line, you will see the URL pattern. So you basically have to provide an X and a Y coordinate, do a GET request, and then you have GeoJSON with buildings. This is the simplest way I've found out how to get hold of building geometry and don't have to do queries or hard conversions and things like that. So it's actually not too hard. Just write a simple script that can run these commands in series, and then you're there. Of course, please be polite. Insert some delays between each GET request. Do not bomb other sites. And then you need to look at the different site, MapTiler, to figure out those coordinates. Okay, it's a little bit of a hassle, but okay, it's still doable. For smaller areas, you're only talking about corner coordinates, and then your script will do the rest. And we must not forget, we have created a mesh object of buildings, but they are not located at sea level. For now, we are just assuming that the floor was at 0 meters above the terrain. I'm sorry, 0 meters above sea level, not terrain. We have to put them on the terrain, else it doesn't make any sense. So what do we do? Well, we read out the locations of the floor vertices, and we have to look up in the terrain what is the terrain elevation at that point. And then we push the floor level to the lowest elevation, so we don't have any gaps. Basically, we just push the building down into the ground, into the terrain surface, until all of those corners on the floor level are on the terrain level or below it. That's a normal way of doing it. The thing is, you lose some kind of precision regarding the building heights because you push it into the terrain. You don't know. The original building height was that above the terrain on the front side or the back side, to put it that way. Was it where the terrain just met the coordinate, or is it how much of the building that's just above the ground? Because what's above the ground can depend on where you are if the terrain is slope. So let's look at this. Here you have a building floating in the air, and we figure out the coordinates, and we calculate the elevation values, and then we just push it down. So there's a little bit of trickery involved in that, in calculating the terrain elevation, because the terrain contains a lot of triangles, let's say 1.5 million triangles, and you have to figure out and interpolate the elevation values inside all of that. But there are data structures that do that very quickly. There's something called bounded hierarchical volumes, and basically what you do is that you read mesh, triangles, into code that creates that data structure for you. And then you can do ray casting. Essentially, like those stippled lines here, you imagine a ray from above at a certain location, and it calculates the intersection between that ray and a triangle, and it does that really fast, and then you get the elevation value out. So it's not a hard thing to do when you use the right code and the right data structures for it. So one implementation of these BHVs is available there. This one is connected to 3.js. You don't have to do that, but at least that's a good implementation, and it's available out there. You can do lots of operations really quickly on big polygonal objects using that data structure. So have a look at that if that's interesting. Okay, back to demo. Let's see what we are. Where we are, what we've got. Yeah, buildings. Okay, Bergen is gone, but at least we have buildings. And this is how they look like. Let's see how we can get, sorry. Yeah, not too bad. Boxy and all of that. All of them are gray. I didn't add any color information here. So that's a bit bad, but okay. At least there are quite a few buildings. I don't know how many tiles I downloaded here, maybe 16 or something like that. Not that many tiles, but at least it gives a decent coverage of the central parts of Bergen, I would assume. Yeah. So lots of buildings, and lots of buildings. More or less like Lego bricks, I would assume. Boxy and all that. So it makes sense if you are at a not too detailed level. But again, this is the best I would assume that you can do using free and open data. Okay, let's have a look. What happens if we add the terrain? We are here, back in Bergen. It's sunny and nice, and we have buildings on top of the terrain mesh. So this is how it looks like. And as we see, the matching is not too bad. The buildings are not in the sea, they are just at the seafront. And also here, it seems to match with roads, depending a little on how the texture actually shows roads and stuff like that. But it seems to be quite a good match between the geometry and the satellite information, and also the terrain mesh itself. And here we can see the small artifacts we had previously. They are connected to the docks here. And here is a bridge that goes on the sea, I guess. Yeah, not too detailed, but okay, this is what you get. It's at 0 level, yes. Okay. Not too bad. So here there are some areas of Bergen that are not covered by these tiles, but it's just a matter of downloading more data. We can have a look here, up in the hill, see how things look like here. Yeah, here we have some interesting artifacts, like buildings that more or less disappear into the ground. That can happen, yes. But apart from that, not too bad. So from a certain distance, this is quite good. Depending on the distance you want to do in your visualization, of course. It can be good enough or not good enough. Okay. So we are reaching close to the end of the presentation. I see my time is almost up, but I have some more minutes. Yeah, packaging. The thing is, what we have been doing so far is just conversion of data and some optimization, but we don't do anything in terms of delivery. How do we transfer these things? If you want to publish information, make a website, have lots of users downloading your data. We want to package things. Basically, there is a tool called GLTF Pack, which is great for that purpose. So if you look at the flow we have been doing here, we have had the terrain from a GeoTIFF converted to an OBJ file, and also the texture was also GeoTIFF. If you want to not lose any information, you convert a GeoTIFF to a PNG, lossless compression. And those two can be inserted into GLTF Pack command, and out you have a GLB. GLB file is a good mesh transfer format that can be used. And also the nice thing about GLB is that it's standard. Lots of tools support it. It has a built-in standard for what the unit is. It's 1 meter. If you look at an OBJ file, the unit can be anything. It's just a number. And also OBJ files don't say anything about which direction is up. So in GLB files, it says that I think its Y coordinate is up. You might agree or disagree or dislike it, no matter what, but at least it says what should be up direction. And that's very valuable in terms of compatibility. And also in GLB, you can do a lot more compression of meshes that we have been doing here. So you can basically reduce the data a lot more. Also, it can support compressed textures as well. So in this case, what I've been doing is I've been combining terrains and textures into a GLB and let the buildings just also flow through the same pipeline. And out we have building GLBs as well. And rendering. Very briefly, I've been using 3JS. The code that runs is essentially what we see on the right-hand side here. I did some simplification, but more or less it's all that's needed to render the imagery we saw. That's because we use a standardized format, the GLB format. So essentially the setup is where you put the camera, which lighting you want to have, and then you load a GLB, and that's that. So it doesn't take a lot of code to render these things. And the performance is good. 3JS does that for you, essentially. So this is not much at all, because we did some processing up front on the processing end, the static end of things. So the rendering is smooth and efficient when you want to display things. Okay, additional tools I want to mention. When you do the development and debugging of things, you want to look at meshes, please use Mesh Lab if you want. It's a great tool to have a look at lots of mesh formats. Do not use the newest version. It crashes on certain GLBs. And we thought that our GLBs were bad, but it was not the case. It was the Mesh Lab that was bad. So use not the newest, but the one before. That's stable and good and nice and dandy. On the right-hand side, there's a tool called QGIS. That's an excellent, I would say, IDE for exploring geodata. More or less, you can drag and drop any geoformat file into that, and it will render it for you. You can just drag and drop in GeoTIFF, GeoJSON, anything, more or less. It can connect to HTTP endpoints. It can do lots of magical things. So as a tool to explore and figure out things, that's very, very, very good. And both of them are free, so just download. They also exist for Mac and Windows and all of that. So good tools I would recommend if you're working in this space. Okay, that was that. If anybody has questions, feel free to come here afterwards. Thank you.